Thank you for keeping an eye on that. Okay. And by the way, I have posted all the lectures so far. I have recorded, and link is on the Canvas. Okay. So again, the B1 is the magnetic field from the current flowing in this wire, blue wire. And that value of the magnetic field is given by this equation here, right? And the direction is given by cross. So that means the magnetic field is going into the screen on this side of that blue wire. Okay. Once we know there is this magnetic field and there is this wire carrying current, for a moment we can forget about blue wire. Forget about blue wire. Just think about magnetic field and wire, second wire, green wire, okay, and current. So now what happens? That green wire experiences force because it's carrying current and it's sitting on the magnetic field B1. So now you can find that by using your right hand rule. So my screen is kind of flat, so I'm making my hand kind of flat, okay? And then magnetic field is going down, means I'm crawling these fingers in the direction of magnetic field down. So that means this thumb gives the direction of force on this wire. Which wire? Green wire. And that force is pointing towards the blue wire. The thumb, my thumb is pointing towards the blue wire. Is your thumb pointing towards the blue wire? Go ahead, try it. Okay. So you line up these four fingers in the direction of flow of current in the green wire. Okay. And then you crawl in the direction, call to the direction of the magnetic field, and magnetic field is going in. Now thumb gives you the direction of force acting on green wire because of the magnetic field produced by blue wire. And my finger, this finger is pointing towards the blue wire, the wire that gave the magnetic field. Okay, so are yours pointing? Are you doing that? If it's pointing right, yes. If it's not right, no in the chat. I can see chat right away. It's on different screen. Okay. Okay. I see a lot of yes, but don't see all though. It is stopped. Only 5, 6 doing that thing in there, crawling fingers. Okay, now I see more. Okay. Okay, great. So that means what's the value of the force? And we know force is magnetic field times current times L. And here the angle is 90 degree. So sine 90 is 1. So it's defined. Okay, so and that's that. So we can see you, Roman. You are trying to figure out direction, I think.
Yeah, I got it. No, I was taking a picture to put in my notes, so that way I remember what I was doing.
Okay.
That's all.
Okay. So this is current times length of the wire times the magnetic field. So current here is I2. This is the current. Remember, I2 is not producing magnetic field. I2 is sitting on the magnetic field. And length of that wire. And now this B1 is coming from the current in wire number 1 or blue wire. And that is given by this equation here, right? So I'm writing that. So that's the force. Force experienced by wire number 2 because of the current in wire number 1. Okay. So if you like, you can write F12 or F21, okay? So now, how about a direction of F? We already talked about. So it's pointing towards the blue, right? So now, so now let's talk about wire number 1 again, but this time it's sitting on a magnetic field produced by current in wire number 2. So when you hold wire number 2 by pointing the thumb in the direction of flow of current and curl your finger, what happens? Again, now I'm talking about magnetic field due to this wire. So when we do that, see, this was from the blue wire, okay? So now I'm talking about the magnetic field due to this wire here. So in this case, what happens? From this side of the wire is coming in, and from this side, it's going into the phase, okay? So since this wire is sitting on this side, so that means this wire is sitting on the magnetic field that's coming out of the screen, okay? It's coming out of the screen, okay? So now what happens? What's the direction of the force? Use right hand rule where magnetic field is B2, which is coming out of the screen, and current in I1 is flowing this way, right? So that's the current, and this is the magnetic field. So with that, use your right hand rule and see which way the current is coming, okay? Sorry, which way the force is acting. Is it towards the green wire, or away? To the green or away? So two choices, right? So go ahead, do it and type to the green or away in the chat. So I'm seeing a lot of greens, okay, towards the green wire. So that's great, yes. So that's how it goes. So now we need to crawl kind of up from the screen. So that means now the thumb is pointing in opposite direction. So that means these forces, the force on this is acting this way, and force on this is acting that way. So that means these two wires, they are attracting each other. They are pulling towards each other, okay? So I don't know if you have paid attention. So if there are like, electric lines going parallel like that, right? So in that case, sometimes you may see there is this wire that's holding these two wires apart in some cases, okay? So it's trying to avoid that kind of attraction, or let's say, it depends on the direction of flow of current, of course. So for example, this is for you guys, let's say homework. Let's say if the current in I2 was flowing something like that. So current is not parallel, but anti-parallel, opposite to each other. How the force is going to act? Will they be attracting? So in this case, the case we saw, when they were parallel, there was attraction, right? So what's going to happen if they point in, if the current is flowing in opposite direction? Will they still be attracting or repelling? Okay, it's for you to figure out. But for meantime, we can write the equation for the magnetic field due to current I2. That means we are writing the value of this magnetic field, and then we can write the force. Okay, it's the same thing. Only difference is now we are talking about force on wire number 1, So that means it has to have its length, and it has to have the magnetic field coming from the another wire. So that's how we can find the force between these wires when their current is flowing. So usually what happens is, for high transmission lines, they have like alternating current. So that means the direction is changing really quickly. So the direction of force is also going back and forth really quickly, okay? But if we were to hang two wires side by side, close to each other, like this, not very heavy wire. So it is ideal. If you want to try this at home, you can do that, especially if you have a battery, okay? And I think it's going to be even better if you have a 9-volt battery, but 1.5-volt battery going to work just fine. So I think you have this, you know, the tin foil wrapper thingy in your kitchen. You use that for wrapping things, right? So the aluminum foil, right? So it's a conductor, so it acts like a wire. So if you make a small strip of one and another one and put them side by side, and of course the current has to be flowing through that. So it looks like you need two batteries and supply current to each of those wires, okay? Somehow you need to connect one side of the, that, you know, tape one side of the that tin the foil on the positive side of the battery, and connect, or you know, tape another side to the negative side of the battery. So that means it becomes complete circuit, and it's going to be current flowing through this wire. Do the same thing, and then hang them, okay? So since the weight is so small, they may be coming closer or moving away. You can actually see that, okay? Okay, so that's about the force. Now here is a question for you. So two wires, current is flowing in the same direction, but now the charge is exactly at the middle and it's moving with speed v, okay? So what is the direction of magnetic force? So this charge now experience force from the current in wire number 1 and current in wire number 2. So force is going to be coming from both. So when we say force on that charge, we are talking about net force, okay, from both. So what do you think? So I'm opening this for poll, and you have 1 minute and 30 seconds to answer this. Oops. So up or top of the page means this. Down. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So the wire current is flowing this way. So because of that, magnetic field due to this wire gonna be dot, 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 coming out from this side, going in from this side, okay? But how about this one here? Because of this. So for this, it's going to be getting out from this side and going in from this side. And since this is exactly at same distance, looks like magnetic field going to cancel each other. There are going to be no net magnetic field there. So if magnetic field becomes 0, then force is going to be 0. But if you want, you can also find the force, and you'll see the force is acting in opposite direction because the V is same, of course, it's the same charge, but the magnetic field is acting in opposite direction, means the force is going to be in opposite direction. I invite you to try which way the force acts because of this magnetic field and that. You can see that. So looks like answer here going to be E. Oh, most of you chose that. Okay, that's the region. Okay, so now here is another question. So now there is this coil that's carrying current, and it's sitting on a magnetic field of the current produced by this. Magnetic field produced by this current here. Okay, so this current is producing a magnetic field, and this one is sitting on a magnetic field like this. Okay, so now the question is, what is the direction of net force on the rectangular loop due to the B field, magnetic field? Okay, so 4 wires, different direction current flowing. So you want to look at the forces in each side and which side there is a stronger force or something like that. Think in terms of that, okay? And I'm giving you 2 minutes for this. If I were you, I'll draw the forces, direction of forces in all sides and see what's happening. And magnitude of force depends on distance, right? Oh, forgot to warn. 20 more seconds, folks. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So in this case, let's see what we got. So mostly I'm seeing C. Let's better be correct. So how do I figure that out? What do I need to look at first? Magnetic field, direction of the magnetic field. That's why let's do that. So looks like on this side, it's going to be coming out. So that's how magnetic field looks like. So this side and that side, they are at equal distance from the wire, right? So this part of the wire, for example, is at this distance, and here, this side, right? So left and right side of this thingy, it is at equal distance on average, let's say, right? This thing here and that thing at equal distance, okay? And how about force then? So current is flowing down here. Current is going down and magnetic field is coming up. So am I getting force in that direction here? And over here, what's happening? Current is going that way and magnetic field is coming this way. Oh, looks like they are pulling towards each other. They are at equal distance means the value of force is same, but they are in opposite direction. So that means these forces on this side, they cancel each other. So they don't have effect, okay? Now let's look at this one here. And this thing is pointing that way. And then field is coming up, means the force is acting in that direction. So let me get rid of other things now. Just look at this. The force here. And force on this one, it's pointing that way. Magnetic field is coming up. So that means the force is in that direction. So again, they are in opposite direction. Do they cancel?
The distance isn't the same between I though, right? So one's further.
Right. So that means distance different means B here is smaller. R larger means B smaller. B smaller means force gonna be smaller. So this force is smaller. This force here is smaller than this force here. So let me make this one bit longer and this one bit shorter. So F net is pointing in that direction. Hey, it looks like C is the correct answer. You guys figured that out quicker than I did. But there was some confusion as well. Okay. So yes, there are, mainly a two-step process. One, you figure out the direction of magnetic field, and then you need to figure out the direction of force. So you need to use both right-hand rule number 1 to figure out the direction of magnetic field. Right hand rule number 2 to find the direction of magnetic field, and right hand rule number 1 to find the direction of force. So you need to use both rules here, okay? So yes, so that's that. So that was about the magnetic field due to wire, straight wire. Now, what if the wire is coiled like this? So what happens is, if we keep the wire straight, it's not very practical. If we want to generate magnetic field, what happens? How long wire are you going to make? So rather than doing that, what we do is we make loop. So like this. So we make loop. So it's going to produce magnetic field. And we are interested in magnetic field at the center, let's say. Okay. So what happens? It's like a current flowing in a loop, like circulating electron, remember? So now it's going to produce a magnetic field. So which way magnetic field going to be pointing at the center? So it depends on the direction of flow of current. Let's say if the current is going something, let's see which one is easy to see. So let's say it's going up there at that end. Then what I need to do is I need to replace that current by my thumb, right? And look at how the magnetic field or my fingers, 4 fingers are curling, okay? Hard to see, right? And you are interested inside. So outside versus inside, it's going to be different. The direction of magnetic field going to be different. Outside versus inside. Because in one side of the wire, these 4 fingers are going in. Other side is coming out, for example, right? It's circling like that, right? So that's one way. But if you are just interested in at the center, then what you can do is you can use second version of this. So just point this 4 finger in the direction of flow of current in the loop. Just grab the loop with the 4 fingers, and now thumb points in the direction of magnetic field. Okay, so it's just a slight modification of right-hand rule number 2. You know, slight modification. So we are switching the fingers. So in this diagram, what you see, this red arrow represents the flow of current in that loop. So that means magnetic field over there going to be pointing which way? It's going to be pointing that way. Do you see that? Oh, right there. The hand is right there. Okay. So that behaves like a bar magnet with north pole like this and south pole like this, okay? But the strength of the magnetic field not gonna be that large if we wanna make it stronger. And by the way, that magnetic field is given by this equation, looks very similar, but not exactly same. Remember last time we had 2 pi r here? Oops, we had 2 pi r in the denominator, but now we have just r, 2r, okay, no pi, okay, you don't get pi here. And n is the number of the turn. So if this is just one coil, 1 turn coil, then n gonna be just 1. But usually what we do is we wind many turns, and that represents the number of turns, and that kind of a structure is called solenoid. Okay, that kind of a structure is called solenoid. So in that case, it's easier. You can just grab, just like I was saying, and find out what's the direction of magnetic field like that. Okay. And when you have large number and something like this kind of structure, what you can do is we can replace this R by the length of the cylinder. So length of the cylinder is not the length of the wire, but here, for example, in this case, this is the length of the cylinder, and this cylinder is a solenoid. We call that solenoid, okay? So the magnetic field is now, it's that, okay? And N over L, number of turns and length of that turn. So if we know both, so for example, let's say there are 20 turns and length is ½ meter, then we can call that number of turn density, okay? So we can replace that by lowercase n and write that as in a simple form. So this lowercase n is just n divided by L. So for example, if this length was ½ meter and there were 20 turns, then the n would be 40. 20 divided by half is 40. So in that case, n would be 40 in this example. Maybe I should write here. Okay, so in that case, that would be 40. So this kind of coil are widely used in, like technology, in commerce, okay? So for example, this one here is a magnetic resonance device that produces image of the soft tissue, okay? So X-rays are used, but the X-rays are used to produce the image of bone, which is harder than muscle. But what if you want the image of the soft tissue, not the bone? Then the X-ray can easily penetrate through that and it's not going to make the image. So in that case, what happens is we use this kind of device, and this device contains large circle solenoid of magnet, and that large current circulate through that produces large magnetic field. Okay, so it produces large magnetic field, and that helps to align the, let's say molecules and so on. And it helps to capture the image. So here, the interest is solenoid. And what's the role of solenoid? It's producing magnetic field. How much is it producing? B is mu naught n times I. I is the amount of current you are passing, and n is the number density of the coil, or is n over L. So that's what it is doing. So now your image of, let's say, your head or soft tissue inside your brain, for example, looks something like this. Okay, so it can produce image something like that. So now here is one question before we move to another chapter. Oh, we way behind in our schedule. Okay, so in this case, you have a minute to answer this question. Oops, only 10 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Oh, almost all of them are C, except one. Can somebody explain why C is the correct answer here? Why is C correct? How did you figure that out?
Okay, I guess I'll give it a shot. If you use your right hand rule and you point your fingers towards that current and you wrap, or your thumb towards the current and you wrap your fingers, it's gonna go into the curve first. So that'll point down, and then if you curve it in on the other side, it'll be up.
Yep, exactly. You made that very simple. Okay, you made it very simple. So can you do that, Roman? I see a loop in your hand. Just use one loop, right? Yeah, okay. Yeah, if you do that, then the curls are going in, right? Yeah. Going in from inside the circle. Mm-hmm. Yeah, so that means that's going to be down. So that's another way to do the same thing. And can you wrap your fingers? Can you wrap 4 fingers in the direction of current there? Yeah. So now you see thumb is pointing down. So that means it's the direction of field inside. So in is down means out must be up. So
right.
That's another way to do it.
Circle back and come back, right?
Right. Okay. Thank you. Okay, so now let's move to another chapter. So to provide voltage, we've been using, battery. We are saying, okay, let's connect battery in the circuit, and that's going to drive current in the circuit, right? Is there a way of generating voltage without connecting battery? And the answer is yes. So how do we do that? And what's going to be the direction of generated voltage? Which side going to be positive terminal? Which side going to be negative terminal? And when connected in the circuit, which way is going to drive the current? So those are the things we're going to be learning here first, okay? So let's suppose there is a wire or just just a flat metal piece, just a metal piece. Yes, of course, this is not metal. I think I had a metal thingy somewhere here. Okay, so I'm finding the metal here. So this is a metal piece. Now we can make it move in magnetic field. So let's suppose magnetic fields, all they are going in, just like we are seeing here in the sketch, right, into the page. So that means, let's say down, or if you are seeing that page vertical, it's into the vertical screen there, right? And now we make it move perpendicular to that magnetic field, okay? And then what's going to happen? So this is conductor, means there are positive and negative charges, equal number of positive and equal number of negative charge in that rod, right? But when it moves in a magnetic field, what happens? It experiences force. Those charges experience force. Remember Hall effect we talked about? It's the same thing here. So positive charge is going to experience force in one direction, and negative charge is going to experience force in another direction. So that means as long as they are moving, they experience force. It's like a moving charge on the magnetic field, right? In the magnetic field. So that means positive and negative charge, they're going to separate. Okay. So in this case, they're going to separate like this, in this kind of configuration. When these charges are moving that direction and magnetic field is going into the page, what happens? Negative charge experience force downward. Positive charge experience upward. So they're going to be positive charge in one side of this rod, positive charge in one side of the rod, and negative charge in the other side of the rod. And whenever we have that kind of positive and negative charge, that means that's how the battery works. In the battery, what happens? There are two terminals. One terminal is positively charged, another terminal is negatively charged. So now this has a charge. In one side, one kind of charge, another side, another kind of charge. So that means it acts like a battery now. So if we were to connect a wire, here, for example, like this, then current, conventional current direction gonna be this. So they're gonna be current flowing. So now we are getting current, we are getting potential difference. So potential difference means the charges are experiencing, you know, the energy there. So where is that energy coming from? The energy on this charge, where is that coming from? Remember, energy is conserved. It cannot come from nowhere. There has to be source. Things doesn't keep, you know, like let's say, what happens to make this rod move? We need to apply force. We need to do work, okay? So that work we are doing is being converted into the electric energy here, okay? So that's how energy, electric energy are generated. The electric energy we receive in our home, we have in our home, the outlet, wherever we plug things, is basically coming from, you know, by generating, it is generated by moving coil in a magnetic field, okay? Here, this is straight, but we make it coil and make it move, okay? So just like we saw in case of Hall effect, it's basically same thing here, okay? We have seen this equation, okay? So that means it tells us how much electric field is generated, and from electric field and the separation distance, we can find the potential, electric potential. So if this was a battery, that means it would be that many volt battery, okay? So electric field depends on the speed and magnetic field. So larger the electric field you want, the wire has to be moving faster, and magnetic field has to be strong. So if we can put large, you know, large magnet with larger magnetic field, but we need to set this wire into motion, okay? The wire has to be moving so that the charge is also moving, okay? So that's how much potential difference we generate. So let's suppose you decided to generate some electricity by dragging this thing. So you connect a wire, make a circuit, and you connect the light bulb here, and then you move this one fast, right? You expect that light bulb to light. Will the voltage generated be large enough? Or if you want to light even a very small power bulb, let's say 5-watt light bulb, how fast the wire has to be moving? We can do a little bit calculation there, okay? And by the way, this E is B times B. So we can write that in terms of magnetic field and the speed, right? Delta V, we can write in terms of that. I'm just substituting that. So this is one equation we're going to be using. So delta V is also called EMF in this case, okay? So VBL, that's the EMF generated by a conductor that is moving with speed V in a magnetic field B, where L is the length of this conductor. That is same as the separation of the charges. So if that's how big this conductor is, if this is how long this is, we say, okay, all positives are piled up here, all negatives are piled up here, okay? So that means the separation distance between them gonna be same as the length, approximately. So that way we can also find, yeah, so yes, that's how they are there, right? So that's the VBL. I think you can find that in formula sheet, okay? Oh, it's written there. So that's the EMF generated by the moving conductor, okay? So now here is a question for you. In this case, it's not talking about value, but the direction, okay? And you guys know clockwise versus counterclockwise, right? So you are looking at the screen and deciding clockwise, counterclockwise. So if it's going like that, that's clockwise. Otherwise, it's counterclockwise. If current is not flowing, there is no current, okay? So you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got. Oh, mostly A. Better that be correct. Am I right? Why? So where are the positive and negative charges on the conductor because of that B and B?
Yes, I said positives would be at the bottom and negatives would be towards the top. Because if you put your hand like this and face it towards the V and then go into the page towards the B, then the force is in this direction. So positive is going down and then negative would be up, and then flow of current conventionally flows from positive to negative, so it would go clockwise.
Perfect. Yes, thank you. So we can also calculate the current. So if R is the resistance, then what's going to be current? Current from Ohm's law, we know it's going to be E over R, right? Have I done that here? Oh, no. E over R means how much is the E? Last slide, we learned that it's going to be B times L times B over R. Did I get that right? With so many equations, I tend to forget. BBL. Yeah, BBL, BLB, same thing, right? Okay. So that's how much current is flowing. So if you know or given those values, how fast wire is moving and so on. So let's do one problem before we take break, okay? It's related to that. If the bulb has a coil of resistance R, what is the power dissipated in the bulb? So we want to write power in terms of B, B, and L. So we just learned current is EMF over R means VBL over R, right? So what's the power then? We know current. Do you know how to write power in terms of current? And resistance is given, current and resistance. How do you write power in terms of current and resistor? Do you guys kind of now feel like, oh, I have seen this? This year or last year? Or was it in signboard when I was driving in I-25? Okay, so it's in the formula sheet and we talk about the power, right? So power can be written three different ways. One is that, another one is V square over R. And another one is, oh, what is another one? I square R, V square over R. Another one is basic IB, okay? So three different ways you can write. And in this case, this B is EMF. So no matter which one you use, you should get the same answer. But current is right there, and resistance, it says it's given, so we can use that, right? So now, let's suppose we want 5 watt. So how fast it has to be moving to get 5 watt? So now we can use that equation. Oops, where is that equation? Okay, so our equation is I squared times R means, what is I? BBL over R square. Whole thing has to be square. That's what I square means, right? And there is R. V square, V square, V square, L square times R over R square. So one of the R cancels actually, okay? So now if we want V, we can solve this one for V, right? So what's gonna be V then? R gonna go and multiply the power. So it's gonna be R times P, and B square and L square gonna come down and divide. That would be V square. So what is V then? That's that, okay? And I think this number turns out to be a large number in hundreds of meters per second. So even to light a tiny, tiny light bulb, you have to make this thing moving really fast, okay? So it's not practical. Theoretically, yes, you can do that, but not very useful. So that's when we start making coils, okay? And look at the spinning motion rather than just going straight line motion. And that's what we're gonna be doing next. And you already know how to find the force, right, on the moving rod. Okay, so let's take a break at this point, I think. But feel free to ask me if you have a question here.
Hey, Mr. Ramesh, so if we have that power, that first problem, it was asking for the power dissipated. Is that an actual number we're actually pulling from that then?
Yeah, that's gonna be this number there. So that means we have to find this. I square means V square, B square L over R square and times R. Okay, yes.
Okay, because I was curious if we were supposed to answer that question before you reached that second half, like without any of the values.
Oh, so if you don't know V, that means how can you find that? Yeah, that's a good point. So other than R is not giving anything. Probably it doesn't expect you to answer that. Okay, but let's see. So yeah, I think you need V. The V has to be given to get that.
Okay, thank you. I was just curious.
Yeah. Here you see that there is V here, L here, B here in this drawing. So this problem is assuming that those things are given to you, okay? And I'm also at the same time trying to write down the theoretical equation, you know, like what's the power equation look like? Yeah, but you brought very good point here though. Yeah. So I'm going to be pausing to record here. Okay, so just like I was saying, that problem gave us the limitation of just moving a straight wire in a magnetic field. Okay, so what do? Is we make a coil, that way we can spin really fast. Okay, so that's how it's done. Okay, so that's what the electric generators are. So what's the difference between motor, electric motor versus generator? Any idea? The motors, they are in the blenders, for example, in the fan, anything that makes rotate, right? The generators are that is used to generate the electricity. Motors, they are consuming electricity. Okay. So in terms of physics, what's the difference? Do you guys, can somebody help me here? Motor versus generators. From that corner there, that corner. So in the motor, what happens? We supply the current. Remember, we plug these devices into the outlet. Electric outlet means current flows through the coil. So when current flows through the coil, what happens? The side of the coil experiences torque. And that's what makes it spin. So current is spinning the coil in case of motors. But in case of generators, we are trying to generate current. So we're not supplying current there. Rather, what we are doing is we are spinning those coils by using something else. So for example, if it is, let's say, coal-driven electric power plant, what do? We use coal to heat the water and convert that water into steam and use that steam. So blow it, okay, on the coil and make that coil spin. And when coil starts spinning, we know it can generate current. Or we can have other sources. Rather than using coal, which is, you know, like it pollutes a lot. There are natural gases. When we burn, it does not emit pollution as much. Natural gases, like for example, propane. That is, you know, when you burn it, it doesn't, you know, emit the pollution just like when you burn coal for the barbecue, right? So same idea there. So very smoky when you use coal for the barbecue. When you use propane gas, not much smoke coming out from the source. Of course, if your meat burns, there's going to be different source of that smoke. That's a different thingy. Okay. So anyway, so you can use that and boil the water, generate steam, and make that spin, blow into the coil and make the coil spin in the magnetic field. More cleaner way is wind driven. So what do? You have seen those big wind wind turbines. So big blades, they are rotated by using the wind, and there is coil attached somewhere there in the shaft. So as they are spinning, coil is spinning in the magnetic field and it's generating current. And that's one of the cleanest way to do it. Another one would be make a big dam and let water fall into the coil and make the coil rotate. So there are different ways you can generate electricity, okay? So in all situations, what's happening? The coil like this is spinning in a permanent magnetic field, okay? So depending on how we are generating, what we are doing is we are just using different sources to spin that coil. So when it's spinning, what happens is that in some situation, when coil is perpendicular, there are going to be maximum force and torque. When parallel, zero torque. So what happens is the EMF generated kind of changes direction. So that's where the alternating thingy comes in, okay? Alternating current, alternating voltage, right? The outlet we get, the voltage we get from our outlet, current we get from our wall outlets, they are alternating. They are generated like this, okay? And transported to our home by using those transmission line. At high voltage, loss of power is small. We talked about that, okay? So anyway, so this one, what happens? So far, we did not have that angle because in all situations, we said, okay, the angle was 90 degrees. But in this case, the angle is changing with the magnetic field because coil is rotating, okay? So that's why we have to have that angle, okay? An angle can also be written in terms of rotational rate, right? So for example, angular rotation is, the angular displacement is omega times t or omega times delta t. Well, let's write just t. Or if we write that delta theta as just theta, we can write that as omega times t, okay? So we can replace that in terms of time and angle and write like that. We learned this in circular motion in physics 1. Okay, this relationship between theta, omega, and t. We wrote delta theta is delta omega times t, something like that. Okay, so that is for the average value. And when we write this, this is instantaneous value. At every moment, that is true. Okay, so that's what it is talking about. So the speed can be written as r times omega. So this speed and that speed is related. So now since we are spinning it, we want to write in terms of omega rather than B. So that's the plan. We want to replace that, okay? So B is R times omega and theta is omega times T. And that's how the EMF you generate is changing, going up and down, okay? That's what alternating means. One side positive becomes 0 and goes to negative side and so on. It's oscillating back and forth because the coil is oscillating back and forth with respect to the magnetic field. That's what's happening, okay? So this is assuming this L as a one side, but there are two sides. So when we do that, you can just double this, right? It becomes 2 times R. And now there is good advantage of this. So 2 times R times L gonna give you the, see, R is like half of the width. So this is like R, oops. If this is width and if it is spinning about this axis, right? So that's the omega. And this is axis, means this is like R. So that R and that R makes 2R, which is same as width. Not W, not omega, but width. So width times length, for example, is the area. So that way it becomes, we have done this transformation in the last chapter as well. We wrote magnetic field in terms of A. Remember I talked about Bina thingy, B-I-N-A or I-B-N-A. So that A was the area. So same idea here, okay? So we want to write in terms of area. So these coils are never rectangular, they are circular. So that way, all we need to know is area of the circle, that's it, okay? Okay, so that gives you the EMF. So this sign is this, see here? Up and down, that's the sine function, isn't it? That's where it's coming from. And this is the amplitude. What's the maximum value we are getting, either positive or negative? That is the omega BA. So when it says, what is the maximum EMF you're gonna get? That means it's just talking about omega B times A. Okay, when coil is at 90-degree position, what happens? You get the maximum value of EMF. And that means this, and that is given in terms of this thingy, just omega B times A. Oh, that's the picture from the inside of hydroelectric generator. So this coil thingy is sitting here inside this cylinder here, okay? So what happens? Oh, no, blade is there. Inside there is blade, and I think the water is coming from this. I don't know. It looks like the wire, those are the wires. So you set up a lot of these generators and you collect the EMF or the current from all these and transmit it to the place where you're going to be using electricity. Okay, so Hoover Dam near Las Vegas, I think this picture, maybe from the inside of that, okay? But I'm not sure at this moment. I forgot to write the source here. So now you can also generate a little bit light by attaching this dynamo, means electric generator in the wheel. So when you are paddling and bike is moving, wheel is already spinning. So now you connect this head of this generator, that means coil is spinning and it's on the magnetic field there. Magnet is right there inside, okay? So it generates that. So now it says, oh, I cannot read that. So number of turns is N, 150, and radius is 2 centimeter. So what do we get from the radius here? Radius of the coil. Is radius relevant for this problem? If we know radius of the coil, we know the area of the coil, right? So that means area is given. Indirectly, area is given, pi r square. So now rotational speed, omega is what? And it says in RPM though. Our formula gonna give omega in what unit? Radian per second. So we need to go from radian per second to revolution per minute. Okay. And we know 1 revolution is 2 pi radians. So we need to use all those information. And EMF is 3 volt, like a 2 dry cells, right? One battery has 1.5 volt, another battery 1.5 volts, so total 3 volts. It's kind of scenario. So, and magnetic field is 0.1 Tesla. And now omega is what? So EMF amplitude means that's the maximum EMF we are talking about. Remember how this thing goes up and down, and that is the max? So that's what we are talking about. And last slide, we saw that is omega B times A, right? So what do we want? Omega means it's gonna be E times EMF times B times A. Oh, maybe I should write E max. That way I can get rid of sign thingy there. Okay, max. So this is going to be 3 there. B is just 0.1. And A is pi times R squared. R is 2.0 times 10 to the power negative 2 square. So no, don't forget to square that. So that makes 10 to the power negative 4, 4 times 10 to the power negative 4. But you guys use calculator, so you can find that. It's going to be in radian per second. So now you need to convert that into RPM. So usually we are used to, you know, like looking at the number in terms of RPM. For example, our car, next to the speedometer, there is RPM value. So when you push gas pedal a bit harder, you see the number. So engine goes, and then this thing spins. Oh, the needle goes like 4,000, 5,000, 3,000 RPM, something like that, okay? So, but this is bicycle. It's not going to be that large. So whatever number you get, that's the radian per second. So radian is just nothing but meter over meter. So radian per second. So you want to get rid of radian. Means it's going to be 2 pi radian in denominator and revolution, 1 revolution. Is that? And seconds has to be converted into minutes, right? So there are 60 seconds in each minute. Yeah, sorry, this bicycle is on the way there. It's just the unit conversion there. So that's how you find the RPM from radian per second. I think we did this kind of conversion in physics 1 when we were talking about spinning motion. Here we haven't done, so that's why I'm doing in detail. Usually I leave these things for you guys, okay? Oh, one thing is missing, sorry about that. 150 number of turns. So this is for 1 turn. If there are n turns, this is going to be n, okay? So it does not have to be spinning that fast because of that n thingy, okay? Yep, sorry about that. And that means you have to have 150 somewhere here. 150 times 0.1 times pi. Whenever I see pi here, it makes me kind of hungry. I don't know about you guys, but that's what it does to me. So now, so far magnetic field was not moving and coil was moving, right? What if we make magnet to move in the coil? Do we get EMF? So physics-wise, it should be same. Remember, here, let's say there are these two things. One, moving means, so right now we may say, okay, the coil is moving away from this rod. We may say that. But coil may say, okay, I'm not moving. Rod is moving away from me. Coil may say that. So they are kind of equivalent situation, okay? They are equivalent situation. So that means we expect to get EMF. And since it's coil full circuit already, we should get current. So here is such demo here.
Current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing.
Did you guys notice the deflection of needle there? And going in versus coming out, that needle is going this way versus that way, okay? So one side is positive, another side is negative. That's what this guy is saying about the positive and negative current, okay? I would say current in opposite direction rather than saying positive or negative. But the ammeter may have that level of positive and negative, one side versus another side. I don't think so. So anyway, that's what it means. So let's watch one more time there.
Changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing.
So right versus left. Did you notice that? Needle deflects a little bit right when it's going in and a little bit left when coming out.
And now let me connect the 100 loop coil.
Hey, N is now 100. Maybe it was 10 before.
Moving the magnet in very slowly. You see a deflection to the right, pull it out to the left. If I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also.
So that's important. So it's not just the magnet and coil, it's the relative motion. How fast it's going makes difference, okay? So that's what we saw. Let's watch one more time.
Change of the magnetic field affects the current also.
So faster versus slower. Let's watch.
Pull it out to the left. If I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnet.
So how much EMF is generated? Which direction it is generated? Again, same thing all over again, okay? So those are the things we're going to be learning here, okay? You change the magnetic field, and we can write that in terms of flux as well. Field times area, remember, and cosine of the angle. We can write that in terms of flux. So when flux is changing, what's happening? EMF is changing. So that's what Faraday discovered. If you just connect this, if you bring that and keep it there, no generation of current, no generation of EMF. It has to be changing, it has to be moving, okay, to generate it. That's what Faraday discovered. So here is one such simple setup. So there is this battery, and this is just switch, right? And this is iron, and this is coil in one side. So when current flows through the coil, it generates magnetic field, right? So when the switch is all the way down there, means current is flowing, constant current flowing. That means it's giving us constant magnetic field. When switch goes from off to, let's say, on to off, what happens? Current goes from maximum to zero, means magnetic field is changing. So when magnetic field changes here, what happens? That change gets coupled to this one here, this side of the coil. And this is just the iron ring here, metal iron ring. So when we have an iron ring like that, what happens? The flux gets coupled more effectively. More coupling occurs. The iron basically, let's say, directs those flux in a particular direction, means in its direction. So that way more flux goes in that direction rather than just going this way or that way, okay? So that's the role of this. So that means we can detect more current. If that's not there, then we may not get as much. So anyway, so that's Faraday's discovery was this one here. This is important. If and only if the magnetic field is changing, and that change can be talked in terms of flux though, okay? So think about this. So this coil, magnetic field here is given by mu times N times I. Remember solenoid we just talked about at the beginning? When I is changing, what happens? B is changing. So how are we changing I on this side? By going on and off. Off zero current, on maximum current. So you see that deflection only when the switch goes on, off, on, off. If it's off all the time, current is zero, no magnetic field. If on all the time, current is fixed, magnetic field is fixed, it's not changing, but it has to be changing to get any kind of induced. So this, what happens here? This coil is not directly connected here, okay? So that's why this process is called induction, okay? Without touching, without direct connection. So the flux from one coil gets connected to the another one, okay? So the flux, we learned about electric flux, B times A times, sorry, not B. Electric flux, we wrote pi times E as E times A times cosine theta. Now for the magnetic flux, we just replacing E by B, that's it. Okay, it's the same thing. And we'll talk about this angle theta. Remember, I think we already talked about once. The theta is the angle made by magnetic field with the normal to the coil. So that's what that is. So if we can make them, you know, like lined up with theta 0, then the flux becomes maximum. And unit of this flux is Tesla times square meter. And this is also called Weber. So if it is inclined, so that's when this angle comes in, okay? So here, the coil we measure the angle from the normal of the coil. That theta we measure from the normal of the coil. So let's suppose this is normal of the coil, and now I have a magnetic field. What happens in this case? When magnetic field and the plane of the coil, they are perpendicular, means, so when the plane is 90 degree, then normal is making 0 degree. So that means in this case, angle between this magnetic field and the normal of the coil 0 degree. They are pointing in same direction. So that's when you get maximum flux. Okay. So it's like saying this. So when do I get maximum flux? So the coil is there. I'm blowing from here. So this is flux of air, right? It's a flux of air coming in. And most of the air goes through this when I keep this coil flat like this in terms of these field of the air. If I make it incline, what happens? Not all of them passes through them. Some of them just gets out from this, right? So that's when it's maximum. So for example, here, see the field are going like this, and coil, plane of the coil is 90 degree. But remember, this angle is measured with the normal. So this is normal here, and we measure magnetic field with this. They are in same direction, means theta there is 0 degree. So plane versus normal. So you may be given one angle or the other angle. So you need to figure out correct angle to use to solve problem, okay? So that's what I'm talking about, that A. Normal to the coil. So coil here, the normal. It's like that. Not this, nope, this. Okay, so that's the angle you are measuring. Okay, so that's the flux. Now, changing field changes flux. Changing field produces induced EMF, means changing flux produces induced EMF. But before we get in there, let's make sure we understand what angle to use. So here is a question. Okay, so in this formula, which angle do you use? Assuming that B is there, and coil is rectangular coil. So that's the plane of the coil. That's the plane of the coil, right? The red is the plane of the coil. Okay, so now you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, what we got? So almost all A, and that is correct answer. Remember, this is normal to the plane. So this is plane, normal to the plane, and this is magnetic field. So this is the angle we are looking for. So now, what's changing here? Area is changing because side of the loop is changing. So flux can change when B changes, when A changes, when theta changes. Now, by how much it is changing? Or maybe not, okay? So you have a minute to answer this question. Oops, 20 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Doubles the sides of the square. Doubles the sides means if this is L, it becomes 2 times L. And B goes from B to half, right? Yes. So length doubles means area becomes 4 times, right? 2L in one side, 2L in another side, 4.
Just do that.
And then B goes B over 2. So it becomes 2 times AB. So AB was already there, this 2 factor in the numerator means up by 2. Did I get that right? Oh, did I look at the result here? Oops, most of them were C. Oops. Magnetic field is not squared. So magnetic field only went half, but the area became 4 times because sides of the square loop was doubled. Not one side, but the sides. I think that's what went wrong. Okay, you assume just, oh, length doubled, area doubled. No, because both of those sides were doubled means became 4 times. Oops. So change in flux, rate of change of flux is equal to the EMF generated. That's it. That's the Faraday law. Negative sign, we'll talk about that a little, later, maybe next class. Okay. So which way it is going, clockwise, counterclockwise, that's about the negative sign, and we call that Lenz's law, right? So we'll talk about that later. But for now, just focus on magnitude. The negative sign simply gives us which way it's going, clockwise or counterclockwise, okay? Current, or if we talk in terms of EMF, that means was the positive terminal generated this side or this side? That's it, okay? This side or this side, that's it. That's what negative sign means. So we'll learn how to figure that out. But before that, let's learn how to find the EMF from this information. What is the induced current? So I is what? So how do we find I? If we are given the resistance, we can use Ohm's law. But for that, we need EMF, and that EMF is not directly given. It's given indirectly, okay? So for that, we're going to be using this here. So how many number of turns there? A coil means N is just 1, right? So N is just 1. And radius 4 centimeter. 4 centimeter means 4 times 10 to the power negative 2 meters. From the radius, we can find the area. So, area is given. Another thing is, this is given. See, what's happening? Magnetic field is changing over time. Hey, time is given. 0.2 milliseconds. So how many seconds? Milli means 10 to the power negative 3 seconds. And magnetic field change goes from 0 to 0.5 Tesla. We can just use delta pi here, right? So delta pi is change in magnetic field divided by time. So final minus initial. So 0.5 minus 0 is 0.5, okay, Tesla meter. Oh, sorry, that's not delta pi, folks. That's delta B, Tesla. Okay, when we multiply delta B by area, that's when we get the flux. Okay, so now I'm coming back up here. So what is EMF then? Number of turn is just 1, right? So I can forget about that. So that means delta phi. So magnetic flux, change in magnetic flux divided by time interval. So that's the EMF, okay? I need R, so let's write R there, R times delta T, okay? Now, delta phi means delta pi means B times A, okay? And the plane is perpendicular means the theta is 0 in this case. So I'm just keeping B times A. R times delta T. So this delta, change in flux can come from 3 different situations. If angle changes, that can change, but angle is not changing here, fixed, okay? This thing and that thing is coming something like that. So angle is fixed. So angle is not changing. Area of the coil not shrinking or increasing, okay? So area is not changing. What is changing? Then B is changing. So that means I can write this as, sorry folks, it's kind of getting more messy. So this delta is in what? A is not changing, but B is changing. So delta B over R times delta T. So now you know delta B, you know A, you know R, you know T. Delta T means you know current. And since we converted everything in SI system, this current better be in ampere. Whew, it went a little longer. Sorry about that. So we're gonna just leave it here. So next class we learn how to find direction.